faces here on the Teams call today. It's been a bit since we've been able to connect as a calm community, so I'm excited to be able to help host these winter lunch and learn events. For those I haven't had the opportunity to meet in person, or maybe it's been a while, my name is Lydia Salas. I'm a project coordinator with the Wisconsin Coastal Management Program. And on behalf of the Calm leadership team, I'm happy to help host today's event. This winter lunch and learn series that we're doing is all about coastline change. And today we're joined by Collin Roland and Chelsea Volpano, who will dive into how the coastline changes over time, some practical uses of their research on coastal processes along Lake Michigan coastline, and then some methods for tracking erosion and sediment transport. So I just want to introduce our speakers quickly before we get started. Welcome to Collin. Collin is a hydrologist with the Rivers and Coastal Processes team at the Upper Midwest Water Sciences Center here in Wisconsin. He's also a PhD student at UW-Wisconsin. And his work focuses on quantitatively constraining sediment transport processes and landform evolution in both fluvial and coastal systems using numerical modeling, geophysical, hydroacoustic, remote sensing, and in situ tools. And then we're also joined by Chelsea. She is also a PhD student at UW-Madison in the geosciences department. And her work specifically focuses on erosion and sediment transport in the Lake Michigan area. She uses imagery, numerical models, and field data collection to monitor geomorphic processes. So we'll have time for questions after the presentation, so feel free to use the chat and put your questions in there throughout. Otherwise, afterwards, we'll be able to unmute, ask questions. We have a raise hand function, and we'll also be able to use the chat after. So I'm going to stop sharing my screen, and I will let you guys take it over from here.
All right, can you confirm that's coming through, Lydia?
Yes, it looks great.
Awesome. Thanks so much for the introduction. Chelsea and I are going to talk about, exactly what Lydia prefaced, coastal changes along Wisconsin's Lake Michigan shoreline. We'll cover a broad range of methods and some of the projects that we're working on. See if I can get this to advance. Awesome. Yeah, so just a little bit about me. I'm a PhD student at UW-Madison. I'm also a hydrologist with the U.S. Geological Survey at the Upper Midwest Water Science Center. I'm a geomorphologist, and I broadly am interested in sediment transport processes in fluvial and coastal settings. And I'll use whatever methods I can employ to try and address those questions and try and measure where sediment's going and how it's moving, ranging from sort of geophysics and numerical modeling to time-lapse cameras and everything in between.
And before I introduce myself, I'm going to see if I can take control to advance the slides. Cool. So my name is Chelsea Volpano. I'm a PhD student at UW-Madison. I got my master's there as well with Luke Zoot. And my research has been also looking at coastal bluff erosion and sediment supply using some of the same methods that Collin does. And then using numerical modeling to investigate nearshore recovery and how those beaches adjust to different water levels, as well as some of the seasonal freeze-thaw processes that are kind of unique to the Great Lakes. So for the methods that we use to collect our data, there's quite a few of them. So we've got a scientific buoy out on Lake Michigan right now measuring waves. We do a lot of GPS surveying to get topographic information, and then we combine that with single and multi-beam bathymetry to get kind of like a cohesive continuation from onshore to offshore of that beach profile or coastal profile. I use single beam bathymetry, and Collin has some information on multi-beam bathymetry with the USGS. That's the first video on the left here. We also use UAS surveying, so drones pretty heavily to make 3D models, again, of the above water portion of the coastline, time-lapse cameras to look at how geomorphic events tie to conditions on the coastline in real time, and then geophysical deployment. So we have a picture of the badgers in the top left here, and those measure basically landslides as they occur. So it extends out a cable, and then when that bluff failure fails, we can get some information on how that landslide is occurring and how long it took to actually fail. So those are just some of the methods that we use for collecting coastal data and investigating some of these processes.
Okay.
And then I'll let Collin take over again.
So just want to make sure we're all sort of on the same page about how coastal cliffs recede. I'm not sure what talks y'all have seen or how many you've been able to attend. I just want to sort of set the stage for the timescales of coastal cliff recession. So over decadal to centennial timescales, we expect coastal cliffs to sort of tend to retreat in parallel. So if you see this figure on the right or upper right, we have the sort of near vertical cliff face and it's just stepping back in time. That's what this progression of lines is. And that's sort of what we expect to see over longer timescales, I would say. But on shorter timescales, we can get differences from that parallel retreat model. The bluff can leave equilibrium. The toe might recede faster than the crest. You might get a steeper bluff, or maybe the crest retreats really rapidly and you get a relaxation in the slope of the bluff. So we have these little fluctuations about equilibrium that are happening on shorter timescales. And that's sort of the story that I'm going to try to tell today, is sort of two looks at those disequilibriums in bluff recession. But all in all, sort of, at the decadal to centennial timescale, we just sort of expect them to step back in parallel. So the first story I'm going to tell is about seasonal fluctuations in bluff recession. So this is some work that we did out in Warnemont Park in Cudahy, Wisconsin. We did, just sort of a shotgun of observations. We put some groundwater wells in, we put some time-lapse cameras out, and we did a lot of repeat structure for motion photogrammetry to measure terrain change at this bluff. It had some pretty active seeps, which you can see by these little blue dots that are in sort of the bottom of this figure. Those are the locations of really active seeps. So this video is really emblematic of what happens at this particular bluff. We're seeing a thaw. There's a little temperature readout on this trail camera. We're getting up towards 20 degrees C when we were at -5 C. We're seeing all the snow and ice start to melt. There's a lot of water coming out of the bluff. And we'll see sort of this, sort of catastrophic failure of the seep here in maybe 5 seconds. And you can see water just pouring out of the bluff as the ice that was maybe blocking that groundwater seepage is melting and allowing water to flow through. So it's really emblematic of what happens at this particular bluff, but up and down Wisconsin's coast and in sort of these freeze-thaw areas, we see lots of erosion associated with freeze-thaw events. So I watched a lot of these time-lapse camera videos and sort of categorized bluff recession in a categorical way, from sort of 1 being little recession to 4 being a lot of recession. And that's what you're seeing in this top right plot. So if the red bar is really long, that's a big erosion event. We can see the erosion isn't sort of continuous. It's rather sporadic. We only have maybe a couple of weeks throughout the year when we have these really long bars. And we can see that they tend to happen when we have fluctuations around sort of that freeze thaw, that 0 degree line. And they also tend to be correlated with precipitation events. So we either have rain or snowfall, or we have decreasing snow depth indicating snow melt. So that sort of gives us an idea of, what you're seeing in the video is also playing out in sort of a more statistically sound way. So we came up with this model of what we think is happening on the bluff. So say during the fall or the summer, water can drain freely from the bluff. We've got low pore pressure in the materials that are sort of back behind the bluff face. We also have sort of, standard shear strength, I would say, because the bluff is unfrozen. But as we start to get colder, frost starts to penetrate into the bluff. We have water that's sort of building up behind that ice dam. So our pore pressure is going up and our shear strength is also going up. So the bluff is getting stronger while the pore pressure is getting higher. Higher pore pressures tend to lead to bluff failures, sort of drive things towards instability. We get this, sort of deep freeze, maybe where we're at right now with the really cold temperatures. We have this thick frost zone. There's a lot of water that might be stuck behind that ice, but the bluff is really, really strong because it's so frozen. So it's not really failing right now. But then when the temperatures start to creep back up, that water is still trapped behind that ice, but the shear strength starts to decrease. So we still have that driving force for failure, but we get this mismatch between the driving forces and the resisting forces as the bluff starts to melt, and that the shear strength in the material goes down. And that's when we see these big failures, and hopefully that's what you saw in that video. That's sort of what we found with this study, and it's not a surprise for those of us that go up and down the coast a lot. We see a lot of failures during spring and during freeze-thaw events, but we hopefully were able to pinpoint one of the driving mechanisms associated with this increase in erosion. And generally, we found maybe 3 to 4 times more erosion, sort of more volumetric erosion per unit time during these freeze-thaw time periods. There are other things that can cause sort of these changes from equilibrium. So this is a large landslide or slide that was associated with a major rainfall event during the May of 2020. This is South Beach in Port Washington. I think they got something like 5 to 6 inches of rain over a short time period, which also leads to high pore pressures and increases the weight on the slope and can decrease shear strength, decrease the tension in the soil, and lead to failures. So we'll look at a slightly longer time scale. I think we all probably know that lake level fluctuations modulate the wave energy that reaches the toe of bluffs, right? Lakes get high, we get more erosion because there's more wave energy reaching the toe. We don't have really good constraints on the exact sort of magnitudes of those relationships. If the lake goes 1 meter higher, how much more erosion do we get, and how exactly can we predict toe erosion associated with lake level fluctuations? So we've done a bunch of repeat surveys at a few sites up and down Wisconsin's Lake Michigan coast. I'll focus on 3 of them here. And hopefully if we do these repeat surveys and sort of measure topographic change over the span of a lake level rise, we can start to constrain and hopefully predict bluff responses. So what I'll show now is profiles, sort of the average profile for 3 of these 9 sites. So South Beach up on the upper left, 2 Creeks upper right, and a bluff in Kewaunee on the lower right. And what you're seeing is sort of the average profile for the site at each time that we did a survey, spanning from some LiDAR data back in 2010 and 2012 up to more recent surveys in 2022. And if you look at South Beach and Kewaunee, you'll notice that there's been a lot of recession at the toe of the bluff. So the toe position has sort of stepped back, maybe on the order of 10 meters, ish, at both of these sort of tall 20 to 25 meter bluffs. But there's been relatively little change at the crest, at least as our most recent data is 2022. Maybe things have changed since then. So these bluffs are clearly out of equilibrium. They're steeper than they were at the start of sort of the most recent rise in Lake Michigan's water levels, and they have not fully responded to all that erosion that happened at the toe. Conversely, Two Creeks has exhibited more of that parallel retreat model. It's experienced toe recession, but it's also experienced crest recession. It's a little bit steeper than it was, but overall much more akin to that parallel recession model, where we might not expect quite as much change in the future. It seems to be more in equilibrium with its current conditions. This is a plot of sort of the average slope for those 3 sites, and just sort of making the point again. Let's see, Kewaunee is in blue, South Beach is in orange. Both have steepened. South Beach is significantly steeper. Two Creeks has also steepened, but it started to come back down. So we would, intuit from this that South Beach and Kewaunee are out of equilibrium, sort of with their stable slope angles, whereas Two Creeks is getting closer to being in equilibrium. And we might not expect as much change sort of being locked in for the crest of that bluff. This is just an example of what continues to happen up and down Wisconsin's Lake Michigan coast. This recent landslide that closed North Beach. A lot of these tall bluffs remain in disequilibrium and have a lot of sort of locked in change that is still making its way up the bluff, which will continue to impact our recreational access, property, like sort of life and limb, that sort of thing. We're still in for a lot of change. The other sort of reason to do these sorts of analyses is to quantify the erosion rates of the bluffs. Bluffs are the major supplier of sand to our nearshore system in Wisconsin. And if you want to be able to sort of close your sediment budget or understand how much beach nourishment you might need to do to close your sediment budget, you need to quantify the value that's coming off the bluff. So how much sand is coming off the bluff. And we could see that sort of these erosion rates peaked as the lake got higher. And maybe they peaked a little bit before the maximum lake level. And that might be because of changes in storminess or sort of other factors that we haven't really quite dug into yet. And so I think with that, I'll turn it over to Chelsea.
Oh, Chelsea, you're muted.
All right, sorry about that. So I'm going to switch over and talk a little bit about beach erosion and nearshore recovery. So Collin kind of alluded to bluffs are the major supplier of sediment, and we're figuring out sort of the processes that contribute sediment to the nearshore, but there's a really big question about what happens to that sediment once it's introduced into the nearshore system. And Collin also mentioned that kind of the nearshore configuration is the main control on incident wave energy. So this is a photo from Point Beach State Forest in Wisconsin. You can see kind of these shore parallel nearshore bars. And those bars will change position relative to changes in lake level and also changes in storminess and wave energy. And they modulate the amount of energy that's able to reach the nearshore. So you can imagine some of the bigger waves are going to break on this first bar here, and there's also another bar that's not pictured that's a little deeper, and so it'll break waves as it comes into the nearshore. And so these bars, this nearshore configuration is really dependent on sediment supply from things like bluffs. And so when we're trying to think about antecedent conditions, so how a storm event might set us up for future changes when water levels rise or fall, we want to figure out how much sediment is available within that nearshore system and how it's kind of moving about. And there's also been this question about where all the nearshore sediment contributed to the bluffs are going. So again, trying to be able to track whether it's going along shore or across shore into deeper water and being lost out of the nearshore system. So for sea level rise, there's a common assumption that's made, which is basically an equilibrium model for sea level or lake level going up, and then the coast retreating an equal amount landward. And the problem with these models is they're more tuned to longer time scales. So long time scales where sea level or lake level is rising very slowly. And so they're not useful on the short-term scales that we experience in the Great Lakes. And it also can't account for that kind of bidirectional rise and fall of the lake levels. There's no real conclusion on how the nearshore adjusts to high or low lake levels, how tightly coupled they are, where that sediment ends up, and basically what this recovery looks like and what timescales we're experiencing. And so I mentioned, right, 90% of the sand here is coming from bluffs. That's this horizontal striped area here. But where is it all ending up? So when we have this continued bluff failure like Collin is researching, where does that sediment end up and why aren't we seeing beach accretion during these times when lake levels are high and lots of erosion is happening? And so one thing that I'm going to look at is the role of nearshore ice and how that changes nearshore sediment availability and nearshore configuration, because this is a really unique feature in the Great Lakes and it has been kind of minimally studied as far as the hydrodynamic interaction. There's been a lot of research looking at how iceberg rafting can carry sediment offshore, but we have some observations that suggest there is another component that influences the sediment budget here. And ice has also been identified as both a protective feature and an erosive feature. So there are some studies that say when you have ice covering the beach, then you're kind of closing off that sediment transport. And there's others that are observing offshore changes when the ice extends out to a certain depth. Again, ice rafting has been the major mechanism that people invoke for the erosion and sediment loss that occurs, but we don't have any systematic understanding of how ice affects the nearshore. And especially with a changing climate, it's pretty important to understand how changes in ice cover are going to affect our sediment budget in the future. And so I alluded to some of this evidence of ice alteration of the nearshore. So this is from Chocolate Beach up on Lake Superior. And so this kind of little snake sinuous line represents some sort of depositional feature, and it matches up pretty well with the maximum extent of ice at this location during this time period. So what we're trying to figure out is what causes this feature and basically how ephemeral it is. Does this stick around? Is this a significant way to move sediment offshore? And so our conceptual model here is that hydrodynamic scour is a pretty big component. So when waves are coming into the shore, they're interacting with the face of the ice that can be grounded into the sediment. And that's causing sediment to be moved in depths beyond what it normally would under the same wave conditions with no ice. So there's this concept called the closure depth, which is basically a depth based on wave conditions over a certain period of time, where beyond that closure depth, you have no sediment movement. And we are basically positing in our study here that the interaction with the nearshore ice face can cause sediment movement beyond that closure depth. So my methodology here is pretty narrow. So I use numerical modeling, specifically this model called XBeach. And this is kind of an industry standard model that folks use to look at the nearshore hydrodynamics and then how that influences the morphology of the coastline. So the setup here is we input bathymetry and wave conditions. We can adjust the grain size and all these different parameters. And then that feeds into the model, which formulates the waves and currents, calculates sediment transport, and then updates the morphology for the next time step. And from this, we can get sediment transport, changes in nearshore morphology, and how the hydrodynamic conditions change spatially. So in theme of the cold weather here, so I have coworkers who have gone out and measured some of the sediment transport occurring in the field and also in the laboratory. So we have a cryogenic wave tank in the lab. And so we were trying to compare our modeling results to some of these observations that they made, but I was able to do it from my computer chair with a sweater on and some tea, which seems pretty alluring during the cold snap. But so we did about 120 model runs. We had several different beach slopes. And then what we did is we used what's called a non-erodible structure, which is basically this impermeable face that opens up to the wave conditions and acts as our nearshore ice. So we would extend it out to a certain depth, run the model, and then change the extent of the ice, run the model again. And then we did that out to about 8 meters depth to the point where we saw very little sediment movement. And so I'll show you some of the results here. So this is for a slope of 0.02, which is a pretty mild slope, but relatively common. And what we're seeing here is the sediment transport and how it's changing with the depth that ice is at. And so what we can see is for the no ice situation, where you might expect there to be more sediment transport because the beach isn't closed off in certain areas, it's actually not the highest point of sediment transport. That occurs some depth offshore, which we found super interesting because you would assume if part of the beach is, you know, completely closed off of sediment transport, that you wouldn't be seeing as much movement. And so what we found was this paired pretty well with the depth of wave breaking. So the point in the surf zone where the waves are breaking relative to the ice depth. And then on this other plot here, we have a kind kind of a spectral representation. So each of these rows represents a model run at a certain ice depth. And then it's kind of looking at things as it goes into the cross shore. We see erosion just adjacent to the ice and then kind of buildup of deposition adjacent to the bar. And we saw this trend pretty consistently for all of the model runs we did at different slopes. And what we found is nearshore ice can increase the volume of sediment transported, and it pairs pretty well with the breaking depth. And then for the steeper slopes, what we found especially significant was that hydrodynamic scour can cause sediment to transport beyond the depth of closure. So this is kind of interesting as far as a mechanism for losing sediment in the nearshore. Just to put it in perspective, this is the Great Lakes average ice cover that NOAA just put out. So all of these little spaghetti lines are different annual ice cover percentages. The red line is the average, and then the black line is where we are currently. And so you can see there's a little bit of a pitch up with the recent cold weather, but we're pretty low compared to the long-term average. And so when we think about changing ice extents, we're more likely to end up at that critical depth where the ice is at the breaking point of the waves and we're seeing more sediment transported. So conclusions for overall, I know we're kind of running over. So we apply a broad range of technologies to the Great Lakes. The Great Lakes system is pretty highly modulated by seasonal processes, both onshore and offshore, and antecedent conditions are really important for understanding the system and how it regains equilibrium. So we have some references if anybody's interested, and then we'd be happy to take questions.
Thank you. A big thank you to Collin and Chelsea for sharing their lunch with us today. What questions do folks have for Chelsea and Collin? We have a few minutes to take questions.
Do you
Or
need
if
us
you'd like
to raise our hands for questions, or can we
raise your hand or just pop in there? You're already off mute, so go ahead.
Okay. I had a question for Collin. You said that where there's active seeps, there were some ice dams being formed on the face of the bluff, but usually fall is such a dry time of year for us. Those seeps are relatively inactive. Did you guys take that into consideration at all, or did you see that at your project site that you were looking at with the seeps, and if whether or not that made it a little bit less of a problem in the springtime when the ice on the face of the bluff was melting or not?
Yeah, that's a great question. In this case, it seemed to be a pretty persistent groundwater seep, like draining, sort of a larger groundwater shed in this case. And we were also doing the study on the back of, some pretty historic wet years. So, 2018, 2019. So I don't think we really saw that influence of the drier weather in fall, but it's definitely could come into play, and especially in these drier years that we've had, that might decrease that groundwater discharge.
Great, thank you. We also have a question from Kiara.
Hey, good morning. Do you have any knowledge of studies looking into long-term effects of seeing less ice cover on the Great Lakes, as far as are we seeing more or less transport, less attenuation of the waves, action on the erosion, anything like that?
So I'm aware of some studies looking at the wave energy during low ice years, and we typically see higher wave energy. I think the question is what, for my study at least, is what the ice very close to shore is doing. And I think that's a little harder to resolve in, because it's such a small area. It's a pretty thin, it can be a thin section along the coastline. I think it's hard to resolve in some of those ice percentage models. But as far as long-term studies looking at the nearshore transport, I'm not aware of any. There's nearshore data is notoriously hard to get. And so I think there's been not a lot of investigation of that.
And has your study, it's mostly started since lake levels have been down, yeah?
Yeah, so I have other field data from a couple sites along the Great Lakes, so a beach and a bluff site, and we've been looking at things since around 2019 at one of those sites. And so we're still in the process of looking at that in the context of all these different environmental factors.
Cool. And you're at Madison, right?
Mhm.
Okay.
Thank you all so much for your questions. Feel free to email me with any other questions that might have pop up after we're done chatting. I'll put my email in the chat here. But just thanks again to Chelsea and Collin. This is, like I said, the first of a couple lunch and learns that we're doing. So please save the date for February 14th as well. Dave Mickelson, who's on the call, will be talking to us about visualizing coastline change. So we look forward to hopefully seeing you.
So thank you all so much.
Thanks, everyone.
Thank you all.